Hi, welcome to today's ADAPT webinar. My name is Spencer Lee. I'll be conducting the webinar today. Just a few announcements before we begin. The webinar will be recorded, so for those of you who wish to view it, just as a reminder, you can distribute amongst your colleagues and peers. It will be placed on our YouTube channel, which is youtube.com/ADAPT-support. And there's an ADAPT webinars folder or playlist there that you can access the recordings from. Also, if you have any questions today, we'll try to answer questions as we move through the webinar. So there's an option in your GoToWebinar panel which allows you to ask a question. I'll try to answer them as we move along. If the question is fairly loaded, then I may just ask so we can answer it outside of the meeting today, and that allows us to kind of go through the intended course and the different topics that we want to cover. If you have questions related to specific model troubleshooting that you might be working on, or other questions that may not be relating to this particular webinar, we just ask that you contact our support group at support@adaptsoft.com, and we can help you through those channels. So we've had a few technical difficulties in one of the previous webinars. If by chance you're unable to hear audio, please let me know. I may have to switch over to a different audio outlet on our end. So I want to make sure everyone can hear what we're discussing. Anyway, we'll go ahead and begin. Today's webinar should last roughly an hour and 15 minutes. For those that need to leave after an hour or so, please feel free to leave the meeting. Again, the recording will be there. So today's webinar, we're going to talk about ADAPT-PTRC and how we can model frame lines or design strips using an equivalent frame program like ADAPT-PTRC. And we'll start by looking at this oval-shaped model, and this adds a little more complexity as compared to, for example, a rectangular or square-shaped model where it's easier to go through and break the slab out into different support lines. So we want to be able to take this particular model and discretize this model into X and Y direction support lines. And just arbitrarily, we're saying that the X direction is quote-unquote banded tendons, and the Y direction are uniform tendons. So in terms of being able to model that inside of ADAPT-PTRC, it really doesn't matter. You just model a strip or a design strip, and that could be for a banded line, it could be for a uniform line. The program gives you the output in both forms in terms of total force, number of strands, or the force per width of the tributary in that program. So we want to talk about determining how to select frame lines to model in a 2D format. We're going to talk about some of the inputs in ADAPT-PTRC, and we won't go through all of the inputs in that program. Many of them are self-explanatory, and we have other tutorials that cover the inputs in more detail. But we will highlight a few of the input screens that I think are common questions amongst our client base in terms of support. So we'll cover a few of those. We want to talk about tendon selection, how the program, how tendons are modeled in the program, where we look at either effective force method, or we're actually modeling the tendon, the calculated number of tendons, and the varying force along the path of a system. So we'll talk about that. And then we want to look at the recycler screen. The recycler screen is really where the user has the ability to modify, manipulate the program's answer or solution. And sometimes the program doesn't come out with the optimal solution. You might have, for example, multiple spans where the two end spans require more force, and you have a chance to optimize where you have add tendons placed on those two outer spans, and we're going to go through that process also today. And then finally, we'll look at just briefly at the output or the outcome of deflections, and also reinforcement. If we run into a time crunch, then what we may do is we'll have to terminate the webinar, and then we can pick up on an additional webinar if needed. I don't think that will happen for today's material and content. So we have this this model, and I'm going to use my highlighter, my marker here today quite a bit, just to try to explain a few things. So in this model we have we're focused mainly on the y direction, the uniform direction. So there's an opportunity for us here to break this into frame lines. Now, if I had just a rectangular slab, I mean, this is pretty easy to take this and to break this into support lines, but we'll go ahead and just compare the process here to what we're doing here. So if I have this slab here, in order to take those frame lines and model them individually in PTRC, I have to determine the path of support. So for example, one path would be along these columns, along this column line. That's our support line or our support path. And then we determine that the tributary for that frame line is something like this. And that ultimately results in I'm looking now at an elevation in a frame line that has 4 columns and a slab. So that's easy to determine, easy to model. And we might have a situation where one frame line that we model in PTRC covers multiple frame lines in a real project. So we don't technically have to model every independent support path or support line. We model representative paths and then apply that same design to multiple paths. And that's a valid approach using the equivalent frame method. Obviously, if you have different loading at different locations, then you might have to make unique models. So for our model here, before we come back to that, I want to show you what we've done in ADAPT Builder. Now, this is our finite element program that I'm looking at. And in ADAPT Builder, we have to go in and we have to make decisions as to what the support lines are in this program. So, for example, in the y direction, I have a support line that basically wraps around the perimeter of the slab on both sides. And then I have support lines that go from column to column to column. So I've dictated the load path for the y direction in this model. When I go through and I generate my design strips in Builder, they're very similar to what you would model one by one in ADAPT-PTRC. So for example, in Builder, if I generate my design strips, and I'm just going to isolate the strips now, I'll show just the y direction here. So we'll go into the graphical design plans, look at the y direction strips. We have this strip on the outside that kind of wraps around the perimeter. It has some defined tributary associated with it, and that is a strip that we want to model in ADAPT-PTRC. So this is just for purposes of showing the strip that we have to model. In Builder, the program takes the actual shape of the slab in terms of designing the strip. In ADAPT-PTRC, which again is the equivalent frame program, we basically have to model this along a straight path, along a reference line. The reference line can't bend, it has to be straight. So we basically take these individual spans and we project them into a straight path. So this becomes, span 1, or this is actually a cantilever on the outside, but cantilever, span 1, span 2, 3, 4, and so on. Each one of these spans has their own segmental length, I'll call it, and we model that segmented length as well as the tributary related to that particular length. So back in AutoCAD, I have an image of that exact strip that we're going to look at today. And we'll go ahead and erase that. Now you'll see I've put some dimensions here. They're fairly accurate. So that's just linear dimensions in AutoCAD and the tolerance in terms of the accuracy. But we have a cantilever, for example, that goes from column out to this point on the edge of this strip. 17.3 feet, 20 feet, and so on. Each of the unique spans has their own tributary, and I'm simplifying this. I'm assuming that the span tributary is prismatic, meaning it's the same from end to end along the entire length of the span. In reality, you might have a condition where you have to segment the geometry in the program. For example, if we have, I'll take this span right here for an example. If this tributary here, instead of going to this point, let's just say the tributary kind of came up like this and then back. We have this panel basically that we want to model. And that panel is shaped like a trapezoid. We have greater tributary as we move from bottom to top. So rather than just modeling the entire panel, the greatest length or the greatest tributary width, we might break that up into segments. 1, 2, let's say 4 segments here. In ADAPT-PTRC, we can do either conventional or segmented input. So we can't model an edge like this. The edge has to be stepped, so it would look something like this. But this would give us more accuracy in terms of a non-prismatic panel than just simply being conservative and modeling the panel for the full tributary width. In our case today, we're going to assume we have prismatic panels throughout. So we have 2 cantilevers and 7 spans. And we're now going to just go ahead and model this strip that we see here using ADAPT-PTRC. Now, the ADAPT Builder program has a module. It's actually the base module of that program that allows us to generate a strip out of here and send it to ADAPT-PTRC. It works reasonably well. I'll be completely honest here. It works reasonably well for very, I'd say, simplified geometry with not a lot of steps, not a lot of depressions, not a lot of beams or drops, kind of a flat slab or flat plate type of construction. Once you get into very complicated geometries, it's probably easier to just model those within ADAPT-PTRC and not try to go through the ADAPT Builder link to PTRC. So we're going to model this relative to the second thing I just described, and that's just basically flat out modeling it manually. So we'll go ahead now and do that. I'll go over to PTRC. The latest version of PTRC is version 2016. And we will be coming out with version 2017 at the end of this month. So look out for that version if you're using this software. PTRC gives you 2 modes of operability. There's the post-tensioning mode and then the RC mode. You can switch models between the 2 easily by switching the mode of operation. So we'll go ahead and run this in ADAPT-PT. I'm going to create a new file. And let me just go ahead and save this over here in the opening screen. So we'll go up here and save the model. Okay, the structural system that we're using will be a 2-way slab. This allows us then to select whether or not to use the equivalent frame method, and when we select to use the equivalent frame method, the program makes necessary adjustments to the column stiffness and the frame stiffness relative to the code implementation. Today we're going to use US units and ACI code. So we'll do 2-way slab. We're using conventional. We talked about segmental a moment ago, so we're going to use conventional input. There are no drop caps, panels, or transverse beams, so we'll select no to that. If we did select yes, then the program has explicit inputs for those types of components and dialog windows allowing you to enter those. For the recommended slab thickness, if you input a span length and you turn this on to yes, when I go into the geometry screen here, if I, for example, put in a span length of 30, the program will indicate a recommended thickness. And this is based on PTI or ACI recommended thicknesses for slabs without checking deflections. the program obviously checks deflections, but we have to use that format for calculating that recommended thickness. So we'll go back. We know what thickness. We're going to use an 8-inch slab for this model. And the codes, if we use US units, all the international codes become grayed out. Our domestic code here, ACI, is the only selectable code. I can use tools to convert units. So if I was to convert these units to SI, then all the codes would then become available in the selection box for the design code. For design settings, I'll make a few comments here that are important. Execution mode, I would always recommend to use interactive. This allows the user to make modifications and changes to the force, the profile, the number of tendons in the recycler screen. Automatic means the program tries to meet all the criteria, and it will automatically exit the recycler screen if it can meet all of the criteria. There's a question. Let me go ahead and answer that. The question is the oval-shaped slab you showed in Builder a real project? The profile looks familiar. The answer is yes, it is a real project. I was given special permission to use it, so I cannot name the project or the company that designed the project, but it is a real project. In terms of the program used to design that, that is not known. So, but it is a real project. So back to the design settings. There's options for reduction of moments to face of support. If you select yes, the program will design to moments at faces of support. Otherwise, no, it would design to centerline moments. We can redistribute moments based on the code allowables and code provisions related to redistribution. And then also we have the set to equivalent frame method. If we select no to equivalent frame method, the program analyzes this just as a direct frame, a stiffness / matrix type of analysis with the ability to increase moments of inertia over supports. So here the program would include part of the column, the joint region. Part of the column is included in determining the stiffness of that section cut over the supports. If we go yes, program again modifies the frame relative to the equivalent frame method. Design options, we want to use all of the provisions of the code in this example, or there's an option to disregard the following provisions. So this does not mean, and I'm going to go ahead and highlight this box, when we say disregard, this doesn't mean that these are the only code provisions that the program is programmed for. This just means these are the only code provisions that you have the ability to turn off or on. So if you select to disregard minimum rebar, that means the program is not going to calculate the minimum reinforcement requirements for a slab or a beam. It's just going to ignore it. It will only calculate rebar for service. This might be important if you're doing an investigative type of a model versus a new design. You can also turn off the check for design capacity exceeding cracking moment. So where you have, for example, a two-way bonded system, you have to meet this particular provision for the ACI code. If you have a two-way unbonded system, then this actually is waived, depending on, I think it's up through version 2014 of the code. So you do not have to meet this for a two-way unbonded system, which is what we're working on. So we'll actually disregard this provision here. And this provision really just takes 1.2 times MCR, where MCR is like the section modulus times F sub R plus P over A. You can't read my chicken scratch here, but this is basically a new combination that is introduced that the program reinforces for when this is not selected. When it's considered, it checks this actual provision. The contribution of pre-stressing in the strength check, if you select this, then program doesn't use any of the post-tensioning in terms of developing or calculating the moment capacity of the section. So you get a lot more rebar than you would otherwise if you leave this alone. We're going to go ahead and only disregard the second option, the cracking moment. So we'll go ahead and turn that one off. One other thing I'll make relative to this input screen is the moment capacity. And this is very important in understanding how the program works. The program is always operating in design mode. So there's really not truly an investigative mode that the program operates in. It's always, whenever you model something, you model a slab, a beam, you model loads, post-tensioning, the program will always calculate the amount of rebar that is necessary to meet the demand moments or factored moments relative to the strength combinations in the program. And it will report in the summary sheet what rebar you need to add to a system in order to meet the demand. Many clients want to use the program for investigative purposes. So they'll model the slab or beam, they'll model base reinforcement, which is just user-defined reinforcement, and then they'll model post-tensioning. So they can pull information off of old plans, outline the profile, the CGS, the force, the rebar, and the goal is to determine whether or not the capacity of the sections as built or as they are existing are greater or less than the demand under maybe new loading, for example. If that is your objective, to do an investigative type model like that, the only output that really is geared towards giving you the information you need is a report, which is report block 34 in the tabular report generator, and that block will outline demand moments, moment capacity, negative and positive. If you use user entered values, this input here, then this means that the report block 34 will produce moment capacities based on user-defined rebar and post-tensioning, not calculated rebar. If you use design values, the moment capacity is equal to that generated by user-defined rebar, post-tensioning, and the calculated rebar that the program has calculated. So this would be for basically new designs. The one over here would be for investigative type work. But again, graphically, if you look at the rebar output, program is always producing the rebar needed to meet the demand moments. So hopefully that's clear to everyone. If not, just let me know. I can try to clarify. So we'll go into the next screen. I'm going to go ahead and just set up the model. We're going to have seven spans, and we do have left and right cantilever. So I'll model this fairly quickly in here. Notice that for each of the spans we have PR, which stands for prismatic. That just means that it's conventional input. If it was segmental, I could actually come here and change this to non-prismatic NP, and that would allow me to then enter segment geometry for a given span. So this is these are all prismatic rectangular slabs, and we're going to go through now and just enter the span lengths. And I'm just reading this off of an output file I have in front of me. These span lengths correspond to those that were given in the image previous in AutoCAD. Now there's a typical row up on top which allows us to, and if I put in 30 feet, for example, and enter, every cell here would be 30 feet. So if you have the same distances, you can use that typical input and take advantage of that, but this is a little bit different. It's unique for each one. The width of the slab is also unique, so we're going to say 151, 167. This is in inches or millimeters if you're working in metric. let's see, 150, and I'm sure many of you have done this before, so I realize this is not super exciting to see, but there are some beginners with us today, so this may be the first time that they've seen this. If I go into the typical for the height, we're going to say it's 8 inches, and you'll notice up here on the top, this is getting filled out with the slab geometry, this window, and you can scroll here and move your mouse and look at different views of the slab. These additional parameters for the geometry makeup are not applicable in this case. We're just doing a flat rectangular slab. If you wanted to change the section type, you can use section selection here, and this allows you to model multiple selections. One thing I'll note, and I'm going to open another instance of the program just to show this. If you model a beam, so if I go into a beam design instead of slab, and I have effective width turned on, this means the program will automatically calculate effective width. If I go over and I try to select an IL or extended T section, these are grayed out. They're grayed out because the program's effective width calculation is geared towards T sections. So the way to bypass that is you have to turn off the effective width option, and now when I go back into the input screen, you'll see I have all of the options available, which means that the user then becomes responsible, I guess, to calculate and input the effective width for the given spans. And you can see, I'm just going to cycle through this. You can see this actually bypasses the effective width window. So if you wanted to use effective width for an extended T or an I section or L section, whatever you're using, you basically have to model that as part of the geometry for the main span geometry. Go ahead and close that, and I'll get back over to my input over here. Let's see, right here. Okay, let me close that so we don't get confused which model we're working with. So I recommend for reference height, if you needed a slab or step segments within a span, you can use this RH value to raise the slab vertically. It just offsets it vertically or you know, positive or negative. For a flat slab like this, I recommend using it, just set it equal to the height of the slab. That means that all of the control points for the tendons are going to be positive upward because they're referenced from this datum, this reference line here. So if I leave it at 0 and they're referenced from the reference line, my slab is below the reference line, so all of the values are negative from top down, which is not, I have yet to see an example of an actual set of plans that show negative values. Maybe there's one out there, but I haven't seen one to date. So I'll go ahead and change that to 8. And the multipliers, this left and right multiplier, let me go to a top view. If you're standing over here on the left side and you hold out your left and right arm, the left edge, I'll call it, is this side, the right edge is this side. And they're referring to the edges out of plane from the window, from the span direction. So when we model a slab, by default, the program has these set to 0.5 and 0.5. And it's taking half, it's taking this times the B dimension, distributing it to the left and to the right. So for example, if I made this 10 and I made this 2, you can see this 151 gets multiplied by 10 and placed on the left side, and then multiplied by 2 and gets placed on the right side, which isn't correct here, but just to show you what this is doing. So for our example, the reason we would want to change this, it doesn't affect the analysis, because the analysis is just a simplified two-dimensional frame. So we're considering flexure and shear. We don't consider any axial restraint or axial deformation. We don't consider any out-of-plane bending. That's the purpose of the equivalent frame method, is to simulate what the response of the frame is if you were to model it, for example, in a 3D or maybe a finite element frame or a skeletal frame. So the purpose of shifting your tributaries really affects the punching shear check and how the program handles the punching shear. So even though the analysis isn't really taking it into consideration, the design for punching shear is. So it's important to set these factors up. So we know if I go back to my image here in AutoCAD, this is an exterior frame line, and the distance from the center of the support out to the edge of the slab we're assuming is 2 feet. It's a constant 2-foot extension, let's say, over the center line of the frame. So because of that, we need to distribute multipliers to the left, which is the exterior side, and then to the interior, this is the right side. And so in the program, we're going to set those up. So I've calculated the multipliers, and we'll go ahead and just enter those. And they're all pretty close. A few of them are different. Okay, so we have our multiplier set for that line, and you can see now the distribution is a little different than what we had earlier, where everything was straddling half and half to either side. So that sets up the frame geometry. I'll go back to an elevation view. We're still missing supports. If I go next, I'll go ahead and enter the supports. We'll just say that the support height for the lower columns is 10 feet. The B dimension, we're going to use 22 and 22. Now, looking at the actual, let me show that in more of a 3D view there. The fourth and possibly the sixth support, if I go back into the CAD file, there's actually walls for supports. 1, 2, it's actually the third, 3, 4, 5, third and sixth are continuous walls in the transverse or perpendicular direction. So we'll go back to the model, and for the third support, we're going to say that the distance, let's see, the B dimension is that in the plane of the slab, so we're going to say that that's 12. The D dimension we're going to just say is 48. I think I have that backwards. Yeah, this is 48 and 12. And we'll do the same thing for the support number 6. We'll say this is 48 and 12. Now, these are modeled as columns. So they're, again, we're not taking into consideration the fact that this is an actual wall that's supporting the slab along its entire edge out of plane. This basically gets discretized into a single line of frame elements with nodes at the I and J ends along this axis. So it's really to the user's discretion how you want to simulate the wall in this particular model. In this wall might be slightly larger, but if I make this wall larger, you can see maybe I'll make it, let's say, 90 inches. The wall just gets placed at the center line of the frame. I can't adjust it in or out of plane. And this is easier to see if I go to a shaded view. You can see there's the wall there, there's my center line, and so this is just discretized as a column, not an actual wall that's extending out of plane. So you want to try to model the wall to simulate the actual stiffness of that support that's there. I'm just arbitrarily using 48 inches just to give it some length, you know, that's different than the length of the width of the column. So if you play around with it, I mean, I checked it at, I think when we were setting this model up initially, we checked it at 48 and then 60 and then 72 inches. and the results were not terribly different in terms of the moments and so on at these supports, but that's kind of a judgment call with how the user would have to set that up. When we model one-way slabs, then that gives us the ability to actually explicitly model a wall, but for two-way slabs, everything is considered a column rather than a wall/column. So you have the ability to adjust the stiffness in terms of a percentage for the supports, and this is just a direct multiplier to the stiffness entries for this particular component in the matrix form. So if I select 50%, then this multiplies and adjusts that stiffness based on this input. We'll go ahead and leave this set to 100%. We'll talk now about the left and right edges. The left and right edges are meant for punching shear. So in the plane of the slab, there's really four categorizations that we use to categorize columns for punching shear. We have, and I'll try to write this legibly. There's an interior condition. There's a corner condition. There's an end condition, and there is a edge condition. And these two are three-sided critical sections. This is a two-sided critical section with two free edges, and then this is an interior. This is four-sided critical section. So the end section, if I have a slab here and I have a column, and you have, bending, let's say there's an axis here and an axis here. If I have bending about this axis, I'll call it X, and this is Y. Bending about X would be the edge condition. Bending about Y would be the end condition. So the program checks both of those at end/edge conditions. In the plane of the slab, the program can determine basically two pieces of the puzzle. So there's four pieces of a puzzle it's trying to determine. It can determine two, let's say. So for this column right here, it knows that, okay, to the left side this is interior, to the right side this is interior, because the program scans and looks and sees if there's a support nearby, and also what's the dimension of the from the column face outward at 4 times the slab thickness. Does it fall within a slab or does it fall outside of a slab? So it knows in this direction what the classification is. But in the out of plane direction, the program has to be given some guidance as to how to check that. So if I go to a top view, you see now I have to tell the program for each column, is this an exterior condition to the left side or is it an interior? And I have to do the same thing to the right side. And so over here for left edge, we know that this is an exterior frame, so our left edge will be exterior and our right edge is interior. When we set this to exterior, what that does is that tells the program, check the distance from the face of the support to the edge of the slab. And let me go ahead and turn this on. So right here is our face of support. Right there, there's our edge of slab. Program checks that distance. And if that distance is less than 4 times the slab thickness, it discounts this. It says this is a free edge along the face of the column, and now I have a critical section that is 3-sided, and this becomes an end edge condition rather than interior. If you use interior condition, and this is a similar condition, you have the same exact condition here and over here, but I have different tags, exterior and interior. In this case, this program says this is an interior condition, use a 4-sided critical section for this. So you would get actually a different result between these two columns by having these two marked differently on each of the columns. So you have to be careful with this. And keep in mind, for a design in which you're using ADAPT-PTRC, you're going to set up a support line that's also going in the transverse direction. So this column gets designed in one direction, then it actually gets designed in another direction, and the user has to somehow collate those results and make sure that both frame directions satisfy the worst case result. Whereas in a finite element program like ADAPT Builder or Floor Pro more specifically, the program is able to handle that at once. We don't have to take two separate frame lines. It just uses the global solution and reactions at the column to check the punching shear. So this is a little more work when you're using a 2D application like this, at least PTRC. So we have those set properly. Let's go ahead and continue. Boundary conditions. This just sets the fixity at the near and far ends. The near end is the end closest to the slab. The far end is the support. So in this case, we have options for fixed, pinned, roller. We're saying that each of the conditions is fixed. It's allowed. We can develop moment at the near end or the near and far ends. The support. This SW. This means support width, not self-weight. In this case. So the support width just determines, that helps the program determine where to cut off the moment diagrams for design. If you use face of moment at support or face of support moments, then this is what's used to determine those cutoff points. Okay, loading, I'm not going to go through loading extensively. Loading, we have multiple classifications of loads, so you have any of these types of loads. Ways to enter those loads into the loading table, I can drag and drop particular loads here. You can see those are drag and drop. I can input the second character in any of the loading tags. So if I, for example, enter Z and then maybe I enter C and M, it will fill out the data necessary to describe this load type on the model. I'll go ahead and just delete those. So for this example, we're going to use just uniform loads. We'll use a superimposed dead load uniform, and we'll say this is 20 PSF. And the live load, we're going to say is 50 PSF. You'll notice by default the program will skip loads, skip live load. And there's 6 different patterns that the program checks for live load skipping. The program will then envelope the results for max and min due to the skipped live load. If you enter a factor, this is the factor that's applied to the live load where and which span it is applicable depending on the pattern. So this is just a factor that's related to provisions in the code depending on the ratio of dead and live loads in the model. This might be set to 0.75, for example. The option to include self-weight is turned on automatically. The unit weight, you'll notice, is 150. If you change the material from normal weight concrete to lightweight or semi-lightweight, be careful because this will update automatically to 90 or to 115. And so you may want to design it for 150 regardless of that change in the material property. So this is something to watch out for. If I select no to include self-weight, then I have an additional classification for self-weight under my loading tags. These are the load case tags that we can assign the loads to. If I go back and select yes, it will actually delete those loads out of the input box. So let's go ahead. Material properties, we'll use 5,000. One thing to be careful of, if you press tab, it doesn't update the modulus. If you press enter, it will update the modulus and recalculate that. For purposes of deflection, the program, we apply a creep factor as a multiplier to the sustained load in terms of getting the total long-term deflections in the software. So again, this is a simplification. This is non-time dependent analysis, so we can't explicitly capture the effects of creep and shrinkage and time dependent effects over different time steps in the software. We have a program that actually does that for frames called ABI, but this is, again, just a simplified version. We'll go ahead and change the concrete. This is the concrete strength that's stressing, so usually we're maybe 0.7 to 0.8 times F prime C here. We'll use 3500. And then for column material, we can input column and beam separately. Again, I have to press enter to update that information for the modulus. For material reinforcement for longitudinal and shear, this is the input dialog for those bars, and this is pretty self-explanatory. Just make sure you set up the proper bar size here for your design. We use number 5s in the slab, top and bottom. And then for shear reinforcement, we have the option for studs or stirrups for punching shear. So you have 2 options there. Now we're going to get into some of the post-tensioning. The post-tensioning, by default, is set as, let's say, effective force method. So for this building example, we'll assume that the tendons are unbonded. The area is 0.153. We're using a 1/2 inch diameter strand. And I'll use the term strand and tendon kind of interchangeably here, but the effective long-term stress, this value right here, is the lower bound average stress in the cable after short-term losses and long-term loss. So we assume that the jacking stress is, let's say, 0.8 times FPU. That gets us down to about 216 KSI, and then we have an additional 40 to 45 KSI in loss beyond that point. And this is what we end up with for our assumed value for final average stress in the cable. So this is the effective stress. There's 2 ways to assume force in the program. You can use an effective value, which just means we're using this lower bound stress. So we take 175 times 0.153, and we get a force of 26.7 kips per strand. The same equivalent force for SI is about 118 kilonewtons. So this is our assumption for each cable that is designed. We assume we're getting 26.7 kips per cable. And that, if we were to graph the force over the length of the span or the length of the system, it's just flat. There's no variance in the force profile. We're just assuming that this is the average force. So we're calling this effective force method in the program. The other option is to have the program actually calculate the friction and the seating loss and the long-term loss. So you might get a force profile that looks something like this, depending on if you have a double pull on either end, or single pull might look something like this. And that's a varying force. That's an actual explicit calculation for the losses, and the program calculates that varying force along the tendon path. So depending on where you're at, you might use one method versus the other. If you're typically domestically here in the US, the engineers are designing per the effective force method for example, for building design. The PT provider, supplier will actually do the calculation for the losses and meet the demand or the design forces on the drawings. In some places internationally, the engineer is responsible for not only the design but also the drawings of the tendon. So they're almost extensively using calculated force method versus effective force. So we give both options in the program, and even here, depending on the severity or the accuracy you want for a given design, you might want to use calculated force if there's a design that's right on the edge of being acceptable or not acceptable based on the design specifications. You might want to use the calculated force also, even when you might otherwise use effective force. So there are 2 different ways to do that. Here, this doesn't change. If you use effective force, the program draws on this value If you don't use effective force, then this basically is not applied in any way. So we'll go over here. Base reinforcement as a user, if you wanted to enter any base rebar, user-defined rebar, you could enter that in this window. We're going to skip that. We're going to just assume that we're going to allow the program to design all the reinforcing. Then we get into criteria. So the program, when it designs the post-tensioning, it has to meet some set of criteria. So it meets allowable stresses, tensile and compressive stress, pre-compression, and balanced loading. These are the allowable stresses that we would input based on the design code. For ACI, we're using 6 square root of F prime C and 3 at initial stress or transfer condition. And then we have our compression allowables. We have our ranges of pre-compression and balanced loading. So we'll say that the pre-compression range is 125 to 300, where 125 might be the code minimum that you can use for a given design. Balanced loading is more of a design tool, let's say, for PT. So we'll say we want to balance 50 to 90% of the dead load in this particular frame. And the program will target a force and profile, because this means that it's sensitive to the CGS of the cable. It's going to target that to meet all criteria, but for balanced loading, we have to try to meet this percentage. This is the calculation option I was mentioning earlier, force method or calculated method. If I switch over to calculated method, this is actually more this is more extensive, because when I use calculated method, when I go ahead and press execute and get into the recycler screen allows you to toggle between force and calculated method. If I select only force method, this becomes grayed out and you can't use this option. So this becomes more extensive in its use. And you can see we can set up friction loss inputs. Long-term loss can either be accounted for directly, meaning it will calculate long-term loss based on these parameters, or if we say no, it asks us for a lump sum value, so this becomes really just an offset of the friction loss curve or the force profile based on whatever value you give for the long-term loss estimate. So we'll say yes to this. I'm not going to go through each of these inputs, but it just what's important is it allows us to calculate friction and long-term losses. These are identified in some of our literature and manuals and technical notes. So for the tendons, there's basically three tendons that we can model in the program. There is tendon A, B, and C. So that's pretty simple. Tendon A always goes from end to end. So there's no shortcutting tendon A. I can't stop it at span 4. I can't stop it at span 7. It's always end to end. There's 2 ways to define the tendons in the program. There's multiple tendon path, which means that we define tendons A, B, and C. We don't have to define tendons B and C, but they're there for add tendon purposes. Or there's a thing called single tendon path. Single tendon path means that B and C become inactive. A single tendon path allows us to have a different force in each one of these spans in the recycler. So it's really just a shortcut way that we can look at a span with a different force, where in reality that would be manifest through use of more tendons in a given span. We're going to look at multiple tendon path today, so that means we want to go back and we're going to use tendons A, B, and C. So when we use multiple tendon path, the force in each span has to be identical. So we have, again, tendon A, and tendon A, let's say that this was a hybrid frame where we only are post-tensioning the 2 outer spans, or let's say cantilever in span 1 and right cantilever in span 7. But the rest of the frame is RC. So in this case, what we would do is we would set tendon A to 0, because otherwise we would have force in all of the spans. We would then introduce tendon B, and we would anchor tendon B back here and run that this way. And we would anchor tendon C here and run tendon C this way. Tendons B and C can be positioned anywhere along the length of the system as long as they cover one span. So I could stretch tendon B if I wanted to back to this point. I could stretch tendon C all the way back to here, and these can be assigned their own unique force. So these are what we call add tendons for the model. And in today's demonstration, we're going to use add tendons here in a moment. So what we have to do is we have to tell the program what profile do we want to use for tendons A. This is tendon B, I'll say this is A, and this is C over here. And we have to tell the program for each tendon in each span what shape do we want to use for our tendon. By default, we're using a reverse parabola. And for cantilevers, by default, the program always uses a straight shape, shape number 4. So you can't modify, or excuse me, for cantilevers, if you leave this set to 1, it uses a cantilever down shape. If you change this, you can change it only to span shape 4, which is a straight shape. So it's really a difference between this to the centroid versus this to the centroid. This is like the first support back here, and then the back span here. So the user sets up the shapes. We're going to just leave these set to reverse parabola. For add tendons B and C, here's our add tendons. There's a tail on the back side of where the tendon terminates, let's say, the support where it terminates at. And that by default, the extension from the center line of support into the back span for an add tendon, B or C, is 0.2 times the span length. That can be modified. This is just, again, just something we start with. So, and we force the program to anchor that add tendon. If this is our slab thickness, here's our support. That tendon comes up high, and then it terminates. Well, I'm forcing it to terminate at the centroid of the slab so that we don't induce a moment where it's anchored. Sometimes that's not possible just due to congestion in the slab. We might have to push it up a bit, but the program gives you the option as to how to anchor the cable. So that's what these selections here are for. We'll go ahead and go next. I'll go pretty fast through the rest of this. The cover, the criteria, we tell the program how we want the tendons to be anchored in the slab. So interior spans, we're using 1 inch from the fiber to the CGS from bottom. On exterior spans, we're using 1.75, and that's for fire rating. And you can modify that to your design requirements. And then for non-pre-stressed reinforcement, we also have to provide a cover. This is the clear cover to the longitudinal bar. So if you have transverse bars in one direction, you have to account for that in this input for this value. The bar cutoff lengths, this allows us to define extension lengths for bar cutoffs for the bars that the program calculates. I'll call this the base requirements. Meaning that just the general default requirements. If you want to get more specific in how bars are cut off and defined, you can basically override these requirements here by using the curtailment input. So this allows the user to tell the program exactly how far each bar should be cut off. You can specify long bars, short bars. This is more in tune with bar diagrams, let's say in chapter 13 of ACI. So for our example, we'll go ahead and just turn that off. We're going to use the default bar placement. And then finally, we get into combinations. So we have basically 4 inputs for gravity combinations for strength or factor, demand level, and 4 for surface combinations. These are used to evaluate the stresses in the slab. These are used to design reinforcement for factor forces and moments. We have input for lateral moments, which we won't really get into today, but if you have a frame analysis and you have joint moments for seismic or for wind and you wanted to include those in the design, you can always enter those into this input for lateral moments and there's 2 additional combos that can be used to evaluate the combination of lateral and gravity. Okay, so that's the input. Now, once we set the model up, the first part of the process is to determine the post-tensioning. So we'll go ahead and model set up. We can go back to any input screen using geometry, loads, material, criteria. That just takes us quickly back to a screen. But we'll go over here to execute and run the model, and we'll get into the recycler window. And the first part of this is the program is determining what the force is and what the profile is to try and meet the criteria for post-tensioning. Keep in mind that the way the algorithm works is it may not be able to meet all of the different criteria options. In other words, you might have such a thin slab it can meet balance loading and pre-compression, but it's unable to meet the allowable tensile stress by meeting the other 2. So you get into a situation where the program gets to a point and then it stops because it can't meet all 3 given the design, loading, geometry, and input. And this is somewhat of a condition that we have here. So when I get into the recycling screen, we see all these numbers and it becomes overwhelming, especially for a new user. And even people I know in ADAPT who don't use this program all the time, they have to stop and think about what this is showing us. So I'll try to explain the key points within the recycler screen. First of all, there's a status window. And this status window up here kind of gives us indication of whether we're okay or whether we're no good, meaning we're meeting our targets for the criteria or we're not. So for the PT force, for example, it says no good max. And I say, okay, so if I look down in the tendon force and height, right now tendon A is selected. So this current tendon, the data from here to here kind of gives us an indication of tendon A, what the current design is for tendon A. We have not set up any force for tendon B or C. So right now our design is basically a single tendon from end to end in the model. And you can see that the program output a force of 656.8 kips. And because of that high force, we have a P/A right here of 544, 492, 446, 413. So every single span exceeds maximum P/A, which we set to 300. Okay, so now we say, well, what do we do? If the only way to reduce the P/A, the pre-compression, is to increase the thickness. That might be the first thought that comes to mind. There's another problem, that the tensile stress is exceeded somewhere. So if we go into tab 4, extreme fiber stress, let me erase some of my chicken scratch there, and I go into sustained loads, I can see that the system is entirely pre-compressed. There's actually no tensile stress at any condition, at any span when I look at sustained load. And we're checking stresses at the left, center, right in this respect. In reality, we're checking stresses every 20th points, but for purposes of evaluation, we only report left, center, right. And this left doesn't mean the extreme left of a span. And let me share this with you. If this is span 1, and this span, let's say, is 40 feet, when we say left, we don't mean like right here. Okay. When we say right, we're not talking about here, and we say center, it's not even there. It's the left has a range. There's a 25% distance. The maximum stress produced within that 25% is reported here. Over on the other side, the maximum stress produced in that range is reported here, and then the center is whatever's in this zone. So those are reported here for stress. So for our design, we have a fully pre-compressed section at sustained load. How can I tell? Well, there's no tensile stress. It's all compression. But if I go to total load, now it's almost all pre-compressed except for this cantilever right. So at the cantilever, oops, let me go back here. So at the cantilever on this end, at the right-hand side of this cantilever, which is actually, or excuse me, the left-hand side, which is the face of support, we have a tensile stress at the top that exceeds the allowable of 6. And that's why we get this flag no good for tensile stress. So we have a few issues with the design that we have to take care of. Now, going back to number 1, tab number 1, we look at the required force. So now I'm looking over here. I say, okay, I have a problem with pre-compression. That's really the major problem here, not the stress. I have a problem with maximum pre-compression. And I look at this required force block. And this required force block tells me how much force is required per location in each of the spans. This value, remember, I said has to be the same if we're using multiple tendon path right here. And I can see that value is actually coming from the right and the left requirements of force for the cantilevers. So those are driving the design, those two locations. In reality, I could say, well, I have a cantilever on one end, a cantilever on the other end. So why not just, and I have a bunch of spans in here, why not just set tendon A equal to the controlling force for all other spans, and in this case it's 434 kips, and then add tendons C and add tendons B for the two cantilevers. So that's what we'll do now. We're going to take this a step further and modify the design that the program has given us. So what I'll do is I'll go into tendon selection and extents, and this allows me to define the location of each tendon. You can see tendon A is end to end, but tendon B, if I press control, I can slide tendon B around. I can move both ends, and the same for tendon C. So notice that I'll go back to, let's see, I'm going to anchor this back even, I'll go the cantilever and then one additional span for both tendon B and C, and those are my extents for the tendon. So I drag these images to the location of my tendon. I can also define it using input here. So for example, tendon B starts at 0 and it goes over to, this is technically in this format, this is cantilever left is span 1, and then span 2, and 25% of span 3, which is in this case 2. It's kind of confusing. So this is 2.2, and I'll go back to my force input. I know that I'm going to change this force to 434 kips. I'll change that. I'll leave the CGs alone for the moment. This is left, center, and right control point heights. And now I'll take the balance between 692 kips, which is shown here. This is what's required at this end cantilever. I'm just going to apply it to both sides. So 692 minus 434, 258. So I'll go to tendon B, and I'll say this is 258. 258. Notice it fills out the cantilever and span 1 because that was my definition of the placement. And then tendon C will be the same. We'll go 258 here. And I'll recycle. If I make a change here, I have to recycle the design. The program will update the results. And if I look at the graphs, by the way, I can see the tendons. So tendon, let me maximize this graph. Tendon A is the red line, tendon B is this blue line, and tendon C is the blue line. So these are the current profiles of each of those tendons. Now, once I do that, my stresses are now okay, but I still have maximum precompression exceeded. But it went down. It went to 359 to 362 on both ends, and previously it was up over 500. So I'm now down in a range that I might be able to say, okay, that justifiably I'm going to increase the allowable precompression maybe to 400 psi. It's not code driven, so it requires a little bit of judgment by the user. But since the allowable maximum currently in the input is set to 300, this still flags as no good. So I'll modify that in a moment, but you'll notice also that the balanced loading now is no good. And the balanced loading, just to mark that, it shows no good here. And I can see for the total, remember, this is current tendon, the total tendons, A, B, and C added together, I have an allowable right there, which is exceeding 90%. So I say, well, how do I control that? What do I do? Well, I can raise the CG at this location to reduce the balanced loading. But before I raise that CG, that CG might have been set to 5.75 in order to maintain the allowable tensile stress at that location. So before I make that change, I'll go to the required PT force input, and I can see that for tensile stresses, this is what's required in terms of force to control the allowable tensile stress. At that location, span 7, I actually have 0. That means that the requirement for the force in that span is actually driven by balance loading and P over A. So that tells me I can make the change to the CG. So I'll just change this to 6 inches, and I'll go ahead and recycle again. And now you can see balance loading is okay. So now my only target that's not okay is precompression. I've made the assumption that I'm going to allow the design to the maximum P over A to creep up to 400, but I still have this flag no good, so I'll exit the recycler. And I realize this is an arbitrary change, but it is a change that sometimes, again, has to be thought through and potentially justified to do for a given design if you're working under other constraints. And this has been done before, so it's nothing that's out of the ordinary, I don't think. So I'll go back to the input under the criteria, allowable stresses. Actually, it's, let's see. Let me go back to P, post-tensioning. And we have allowable stress. And then for maximum precompression, I'm just going to change that to 400. And I'll go back to the recycler. Once I change the input, the program recalculates the result. So you're going to see when I go back in here, we're going to potentially have other stuff that's no good. But what I can do is just recall the previous result and recycle again, and that gets me back to the design that I had set up in my previous example. So going back into recycler here, we'll be able to see that. Okay, so you can see that this says no good and no good again. Basically the same exact design that the program spit out last time. If I select recall and recycle, this will set me back to what I had previous, and we should now have an acceptable design. At least I think. This is 300. Oh, I'm sorry. This total P. I was focusing on tendon A. This total P over A is still high, so I apologize. That I was forgetting to add tendons B and C. You can see that this is still much greater than 400 on these two outer spans where I added tendons B and C here and here. So what would have to be done for this design potentially is to actually thicken the two cantilevers on either end to reduce the amount of P over A there, because I need this force to control the stress. So I have to do something other than modify the tendons or the allowables to meet the acceptable design limits, and in this case it would be to thicken the slab. So my apologies for that. Let's go ahead and exit. I'll finish up now. Once we exit the recycler, the program goes into a couple of post processes. One is reinforcement, the other is deflections. So we know what the PT is, then we can go ahead and design and calculate reinforcement, and we can also calculate deflections based on the set profiles and force for the post-tensioning. In terms of reinforcement, just quickly I'll mention the best place to look at the final design is if you open this builder sum or the summary tab here. It's this little yellow tab. That opens a module called builder sum, and for the envelope of the design we can review the reinforcement for the given span. So we have top reinforcement shown 7 number 5s by 10 feet by 13'5" or 13'6", 14, and so on. And this is likely controlled by minimum reinforcement. I can tell if I toggle this over to service rebar, or excuse me, service max or min, this will indicate how much rebar is actually required to meet the minimum reinforcement requirements for a 2-way PT slab. So this is now only the reinforcement necessary to meet this particular requirement. For strength, if I go over to strength 1 minimum, for example, you can see there's some requirement here to meet the strength requirement, meaning the demand moment over supports. So this is the requirement there, but this may not be more than service. So as a user, you can look at these different results to determine what's controlling at where, at what location. But ultimately, the rebar is produced in this format, the summary format for top. And notice that this design does not require bottom reinforcement. So this means that the stress in the flexural tension zone for positive bending was less than 2 times the square root of F prime C. And that was actually shown when we were in recycler. The compressive compression was controlling most spans other than those 2 locations at the top of the supported cantilever. So this design actually doesn't need any bottom reinforcement. The strength is, the resistance is actually given by the concrete and the post-tensioning for this design. Additional locations for reinforcement would be if you go into the tabular report generator, we can go into a compact or a detailed report, and in these 2 reports we can go in and generate a solution for mild reinforcement, which is block number 10, and then detailed rebar block 29, and that will show us the required provided rebar for every section along each of the spans in a tabular type of an arrangement. For deflections, graphically, if we go back to this graphics view, this just shows us some different graphs for moment shears. If I go to deflections, this is going to graphically show us service total and service sustained deflections for the system. If we maximize the graph, it's a little easier to see those values. One of the other options is, again, in the summary sheet for the design. If I go to the second page here, this produces both the graphical result and also a tabular result. So if you're used to, or if you've used previous versions of the program, previous versions from 2014 and back, the program never included a portion of the live load as part of the sustained load deflection. So in the latest version, 16, 15, and 14, we modified this such that For sustained load combinations, which are combination blocks 1 and 2, total load combination blocks are 3 and 4. So you can see we have a combination here. This is combination 1, combination 3. This includes the, this captures live load as part of the sustained load output. This does not. So the way that this sustained load deflection is calculated, it's 1.21. What's happening is it's taking 0.74, and so I'll write this out here, 0.74, and it's adding the creep 1 plus the creep factor, which in this case was 2, and it's multiplying 1 plus creep factor, so this is basically 3. So it's 0.74 plus 3 times 1/3 of the live load. If you recall, this combination is set to 0.3 times live load. So we take 0.52, that's the live load deflection, times 0.3, and we apply the creep to that, and that's a factor of 3. And then we add that to this 0.74, and that gives us this deflection of 1.21. The total deflection takes 1.21, and it adds the additional 70% of the live load. So if we take 0.52 times 0.7 plus 1.21, we get 1.57. So that's a little bit different. The reason I'm explaining that is it's a question we get commonly in support, and it's different than what you might be used to if you've used previous versions of the program. For service combinations 3 and 4, we don't do that. We don't include live load as part of the sustained load. So here, the sustained deflection is just 0.74. It's whatever it is. The sustained in this case is just dead load plus superimposed dead load plus PT, and then we apply the creep factor. That gives us 0.74. That's shown here, and then we add the 0.52, and that gives us the total. And so this is historically how the program calculated the deflections without the inclusion of live load as being sustained. So this is a little different, again, than what we've done in the past. Hopefully that's helpful in understanding that. We'll go ahead and conclude now. If any of you have any questions, please feel free. I'll wait a few minutes here to see if there are any questions. I appreciate everyone taking time today to join us, and if you have any questions outside of the meeting, please feel free to contact support@adaptsoft.com. So I'll go ahead now and take questions if there are any, and you'll have to type them in, and then I'll go ahead and answer once I see them. There's also a hand raise option. If you raise, it looks like Adam, you might be wanting to ask a question. Go ahead and type the question in if you have one. Okay, looks like there are no questions, so I'll give it about one or two more minutes and just wait here. For those that don't have questions, feel free to exit the meeting, and again, the video recording will be placed at youtube.com/adaptsupport. All right. Again, I appreciate it, everyone. Thanks for attending today, and thanks for using ADAPT. Have a great weekend.